Hello, welcome to Sisyphus, Crane and Rigging. I'm starting a series on the first RollingBall lift. This is Mr. Bix and welcome to my channel. It's a massive Kinetic Art build. This is video number 2. It's the first of 3 on a ball lift, the Eponymous. Kinetic Art, in one popular form, is machines built for entertainment that move. Probably some of the most popular and frequently seen are rolling ball sculptures. Of course, that means balls rolling around on tracks. I love to build them, and I go way back. The original Kineticon had a loop in it, which a loop-to-loop where the ball would go running down the track and through this loop. It was fine until the ball would fly off and smack against the glass from the inside for no apparent reason. I mean, I did realize that the marbles I was using were notoriously imprecise. They weren't very round, as spheres go. But even with a ball bearing, the stochastic law of falling off took over, and it would scare people to death when a ball flew right at them at high velocity and smacked the glass. I ended up building a sort of a spiral, which was safer. It worked more reliably. They never fell out. There is a lot of stuff out there on rolling ball machines. I've got some links below, and if you start searching, you'll see there's a bunch. I've built some tricky machines myself. I even won a major award. I like the idea of building tricky mechanisms to carry the ball up. So I'm challenged by making more interesting lifts. In this sculpture I did called Curves and Extrapolations, my lift system consisted of linear drive screws and carriages that had these sort of plunger ejector mechanisms that actuated at the top of the travel, knocking the ball out into the ramp, or at the bottom, causing another basket to swing up and load a ball into it. And this was done in 2002, about the time of the Winter Olympics, hence the colors yellow, orange, and blue, which represented Utah's colorful landscape. That led to a personal challenge to do something unique, something different for the new Kineticon. My idea was to build a bucket to descend down and grasp a ball. The prototype had this internal latch tongue mechanism, which would be tipped into place by this surrounding bale that hits a post or a fixed part as it's lowered onto the ball. At the release point, the bale would be tipped the other way after it had picked up the ball and carried it to its location. And when it lowered, it would hit the fixed point again, allowing the jaws to open and drop the ball. Maybe someday I'll get that to work, but it's as fussy as it can be. When something like that ends in failure, you question whether you can even pull it off. Maybe the whole idea is now in jeopardy. I bought a Lego kit with a crane bucket to see if that would inspire me. At the best, though, I put it on the shelf for a while. The original idea was just to get something that could pick up the ball and set it down on top of the hill. This crude model that I made in SolidWorks gives the idea, but it doesn't give anything away about how it's going to work. After wondering for a while whether or not I was even going to be able to make it, I realized that sometimes it helps to break it down to the simplest possible terms. Now I'm looking at the motions it will need to pick up the ball and deliver it to its place on top of the hill. There are 4 degrees of freedom, if you will, and I realize I need a gripper, which requires 2 wires just to run the motor, dedicated wires since the polarity changes and it'll need to run it forward and back, and 3 wires for the switches, an up limit switch, down limit switch, and the common for both. When I get to the Z-axis, I realize I've got to add 4 more wires, 2 more dedicated motor polarity wires, and 3 more switch wires again. Although I can save a common on that. So that's 4 more wires. Same thing for the Y-axis, it adds 4 more wires. And then the Z-axis will carry all of this back and forth. Although it adds 4 wires itself, they're fixed to the table. So I've started to build it. I'm going to give you a detailed explanation of how I make the parts. I'm looking for something that looks like that, and I found this gripper on the internet. It looked like something I could build, so I go ahead and get an image of that and put it into SolidWorks. Trace right around it so that I can model the part from the sketch. And I make the parts in such a way that I can get a working, functioning model in SolidWorks. And when it looks like something that I want to try to build, I do drawings so that I can take it over to the milling machine. And I also export a DXF. I take the DXF and I send that off into a nice 80s and 90s technology called the floppy disk. I don't know if you remember those, because I'm going to be doing a couple of sneaker transfers here. I take that over to an old Windows 98 machine that I keep running for just this purpose. That's the DXF there. And load it in so that I can bring in a model that I can use. I'm using CAD Key 99, an old drafting program. Watch out, SolidWorks. And there's the 98 machine. Screensaver's the Doll's House in the Maze District down in Canyonlands in southern Utah. I bring this thing into CAD Key. I make an offset, that's the red line for the toolpath. Save a DXF of that. Put that over to the Easy Feature Mill, which is an old kind of a Mastercam software. Watch out, Mastercam. That yellow is the toolpath simulation. Save the NC. Quickly run it over to the milling machine. Load it into the milling machine using nice modern technology and program that into the mill. So now I'll be able to run that path, and I can make modifications or do anything I need to, but it's a quick and dirty way to get a 2.5 axis CNC pattern into the milling machine. A quick way to get my metal shape outlined is to just tape a 1-to-1 print that I've snipped out onto the metal. I put that in, drill the 3 holes that are going to hold it down, and I screw that down with, these happen to be 256 screws. I use a drill bit that's just barely bigger so that I get a nice tight hold on the brass. Working with the brass, it's thin material, so I don't have a big need to pre-cut the part. If it were not so easy to just run the profile on it, I probably would take it over to the bandsaw or whatever and take a lot of that scrap around the edges off. So I screw it down nice and tight, and with a 1/8 inch end mill, I come down on it and start making passes. I just repeat the program several times. The brass is rather grabby. I'm using a 4-flute end mill and taking several passes around the outside with a couple of thousandths extra on the offset. And then when it comes down to it, the final program is where I want it to be to get a finer surface on the brass. And even at that, it's got those little chips in it that you get with milling brass, because it is a grabby material. And I guess I gotta look and see if there aren't end mills made for machining brass. So a little bit of post-finishing on the part, and actually on my final build, I'll pre-finish those parts, including getting them plated. In fact, these little brass parts will probably get gold plated. You can also plate in brass, but it tends to tarnish. So there I have them laid out, and that back plate is what they're mounted on and has a slot for that top driving pin to be guided in. I made a SolidWorks drawing so that I could see which parts get the pins. Otherwise it's confusing. It's like I say, it's working out a puzzle. And there it is assembled with the pins, and a quick test just to push it down to see that it works. Now I have to dress the ends, take those bosses off. In SolidWorks, I modeled another little piece around this end area, which doubles the width. One goes up and one goes down because they're offset. Drill a hole in it for that 80 screw. And then I silver solder that width onto it so that I have a better boss on which to attach the cup. You can see the silver solder flowing into the joint there. Cut it off with a saw. Yes, I did let it cool. That would have been a hot grab right there. And I dressed the end of it with the end mill, both for flatness and the edge of it. And again, this will clean up even more before I do the final reassembly. I drilled it out for that odd 80 screw. With the brass, you want to go nice and slow. Even on a small part like this, it's very grabby. And check the screw fit. So now I wanted to make the cups. I use a Holdridge milling, radius milling attachment. And that's a sweet tool to use. You set it up on your lathe and take most of your time dialing it in. That's the main part. And very carefully move the Z-axis into the part and swing that thing. Let's speed it up, but it goes pretty quickly. Take out a radius to the size that you've set on that tool offset. There's the final pass, and she's good to go. Do a facing operation. Now I've got to get ready to trim the back side of that to make the actual sort of dish. So I'm coming in, I've already set the compound at the angle that I want, and I'm coming in and moving back a little bit, long enough back, far enough back on the Z so that I can take this down to the diameter I want. And it's very small. I was down to about 1/10 of an inch on the diameter. You don't quite see that final diameter turn, but I do come back, and then you draw back with just the compound at the angle you want to get that edge you need at angle. Never did part it off on the lathe. I take it over and saw it off with a handsaw. And of course, even though I'm holding it, dropped it, have to go find it. Then that gets tapped for the odd 80 screw. So this is an assembly in SolidWorks, and I use the mates to mate the faces and then do the concentric mates so that you align it and put the screw into it. When you do that in SolidWorks, you really know what you want to build. So then we screwed those things together. And I'll use a drop of Loctite when I do them the final time. There are 2 of these arms. Like I said, they're offset. One of those added tabs has to be on one side, the other has to be on the other side, or it simply doesn't line up. And that would be the wrong side right there. It's not going to grab the ball, but if you put it on the right side, it matches perfectly and it grabs the ball. So it's easy to model in SolidWorks, and that slot keeps the center pin, the driving pin, aligned. And that's what you're going for, a gripper. It doesn't take very much movement for that action to happen. So I got all the parts laid out, and I did it several times, but each time it seemed like a puzzle. And this is where you've got to remember which way they go, or put it together in such a way that it'll work. Then you know you've got it right. Uses a shoulder screw. It's ready to rock. And there's a final pickup. That wraps it up for this video. The next one will be the Z-axis, the Y-axis, sliding contacts, and some of the fussy details that go with that. Until then, this is Mr. Bix, and as I often say, is it not absolutely original?